As our second example of a max-min problem, let's do this one. This is problem number 20 from page 225 of the book. A rectangular solid with a square base has a surface area of 337.5 square centimeters. Find the dimensions that will result in a solid with maximum volume. To kind of get our hands on this, let's maybe draw a picture of what we're talking about. We have a rectangular solid with a square base. So it looks something like this. If we want to, we can sketch in kind of the hidden parts back here. Since the base is square, these two edges have the same length. So let me label them both with X. The height might be something different. So I'll label that with Y. Now, I've kind of summarized our method over here. We want to write down the objective function and constraint. So substitute this constraint into the objective function, take the derivative, find the local extrema, and then interpret the answers. So first of all, let's write down the objective function and constraint. Remember, the objective function is always going to be something you're trying to maximize or minimize. So here we're trying to maximize volume. So our objective function is to maximize volume. And remember that the volume for a rectangular solid is length times width times height. So that'll be x times y. So x squared times y. Now there is a constraint. The restriction is that the surface area is 337.5 square centimeters. So surface area is equal to 337.5 square centimeters. Let's see if we can write down the surface area in terms of x and y. This rectangular solid has 6 different faces. It has a top and a bottom, and the top and the bottom are squares with side length x. So we have 2 faces whose area is x squared. Notice that the area of the front face is x times y, and there are 4 faces that all have that area. So the surface area of the entire solid is going to be 2x squared, that's the top and the bottom, plus 4xy, the 4 lateral faces. So, step 2 is going to be to solve for one of the variables in the constraint and substitute into the objective function. Notice here it's going to be much easier to solve for y than for x. So let's do that. This was step 1. So solving for y in the constraint, we're going to get 4xy equals 337.5 minus 2x squared, and then dividing each side by 4x. Y is 337.5 minus 2x squared all over 4x. And then we want to substitute this in for the y in the objective function. So we have v equals x squared times 337.5 minus 2x squared over 4x. Notice here that this is a function of only one variable now, so I can emphasize that by writing this as v of x rather than just as v. Now I am going to want to take the derivatives, but before I do that, let's simplify a little bit. I can cancel one of these x's from numerator and denominator. So I cancel this x with one of those. And then I can distribute this x into the numerator. So that'll be the same as 337.5x minus 2x cubed Now remember, when I take the derivative of this, I don't have to use the quotient rule because the denominator is a constant. So I can just differentiate the numerator. So the derivative of the numerator is 337.5 minus 6x squared, and then divided by that constant 4. Oops, yeah, that's right, 6x squared. So there's no place where this derivative is 0. So there's no place where the derivative is undefined, since the denominator is non-zero. To find out where it is equal to 0, though, where the fraction is 0, I need to set the numerator equal to 0. So 337.5 minus 6x squared equals 0. 6x squared is 337.5. X squared is 337.5 over 6. So x is plus or minus the square root of 337.5 divided by 6. And that looks weird, but actually it simplifies to plus or minus 7.5. So these are going to be the points where this function here has its relative maximum and minimum values. Now remember though, x represents the side length of one of the edges of this rectangular solid, so a negative 7.5 doesn't make any sense. So the only critical number that it makes sense to use would be positive 7.5. I'm going to kind of almost box that. But let's check and make sure that this really does represent a maximum as opposed to a minimum, because I'm trying to maximize the volume. So to figure out whether this is a max or a min, I can use the second derivative test, which means taking another derivative of this function. So v double prime of x, once again, the denominator is constant. So I'll just take the derivative of the numerator and divide by 4. The derivative of 337.5 is 0, minus 12x. So the second derivative is the same as negative 3x. So if I take the second derivative and I evaluate it at my critical number 7.5, I get negative 3 times 7.5, which is negative. So at the critical number, the second derivative is negative, which means the graph is concave down, which means that I really am at a relative maximum. So let's take care of the interpretation. So a maximum volume is obtained when x is 7.5 centimeters. Remember to use the units. To figure out what y is, we can substitute into the constraint here. So y will equal 337.5 minus twice 7.5 squared over 4 times 7.5. And maybe surprisingly, maybe not, that also ends up being 7.5. So the dimensions of the solid are going to be 7.5 centimeters by 7.5 centimeters by 7.5 centimeters. In other words, we've got a cube, and the volume will be 7.5 cubic centimeters. Now that actually completes that problem, but let me point out one variation on this that you may see in one of your exercises. And it'll be very similar. It'll say a rectangular solid with a square base, but it might say, and no top. So, in that situation, when you have no top, then you only have 5 faces. We have the square on the bottom, and then the 4 vertical sides. So the only thing that changes about the problem is that the surface area becomes 1x squared plus 4xy. And then you'll substitute in and do the rest of the problem exactly the same.